Hi guys, we are back and we are going to keep continuing to add to our list of integration techniques. So we looked at trigonometric substitution. What we're going to do now is look at something called partial fractions. So let's head on over there and see how this works. All right, so we're talking about partial fractions, and let's motivate it with the following. So let's say I had this integral. Let's use blue, such a gentler color. Let's say I had the integral of x over x squared plus 1 minus 3 over x minus 5 dx. Now, I think you'd probably look at this, and your first thought would very correctly be to break this up. And minus the integral 3 for x minus 5 dx. Now, for the first one, you'd probably do a u substitution. U is x squared plus 1. So du would be 2x dx. And what happens here? Well, you'll have, maybe on the second one, you'll do u equals x minus 5. Du equals dx. And so what do we have? We'll have a 1/2 du over u minus 3 times the integral du over u. And we know what this is. ln absolute value x squared plus 1, because that's what u is. I know that's a little redundant. That's okay. And minus 3 ln absolute value x minus 5 plus a constant. Okay, pretty straightforward. Well, let's say we had this example now. If we had this situation, negative 3x squared plus 3x minus 4 all over x cubed minus 5x squared plus x minus 5 dx. Okay. Now, when you look at this, it's not so simple. But what I want you to think of this as, I want you to think of this as some collection of rational functions that has been added together with a common denominator. Well, in order to figure out what the individual denominators might have been, I can take x cubed minus 5x squared plus x minus 5, and I can simply factor it. And so if we do that, let's see. Well, I can think about my rational roots theorem. If I think about 1, let's see. If I let x be 1, then 1 minus 5 is negative 4 plus 1. Oh, that doesn't work. But, oh, I see what we can do. I can rewrite it as x squared times x minus 5 plus 1 times x minus 5. And so I've got x squared plus 1 times x minus 5. And so what I can do is I can think of this denominator, my whole integrand really, as coming from some combination of x squared plus 1 and x minus 5. And actually for just simplicity of my own labeling, I'm going to put this x minus 5 first. Now, we might look at this and say, okay, well, we got fractions. Let's think of these as proper fractions. So from a polynomial perspective, that means the numerator would have to have a lower degree than the denominator, which means for my first rational function, that's just some constant. now I've got x squared plus 1 as my second denominator. And in that case, I'll have a linear numerator, bx plus c. And so if you think about what it would take to get a common denominator, well, you'd multiply x squared plus 1 times a, and bx plus c would get multiplied by x minus 5. And what you get would be this numerator, negative 3x squared plus 3x minus 4. Now, what does this do for me? I'm not going to actually finish this problem, but I want you to at least see it. So bx squared, and then cx minus 5bx minus 5c. And now we're just going to factor accordingly. And regroup. And so what I'm going to do is I'm essentially going to equate coefficients. There's other ways to do this, but I can at least notice that, right, my coefficient of x squared is a plus b. That should be negative 3. My coefficient of x is c minus 5b. That should be positive 3. And my coefficient, or my constant term rather, is a minus 5c, and that equals negative 4. So you have a system of equations here, and you can very easily solve these. And what's interesting is that if you do it correctly, you'll get a equals negative 3, b equals 0, and sorry guys, b equals sorry, I did this backwards. I'm gonna let you guys solve it out, and I will come back and tell you what it is, but I want you to try to work it through before I just kind of tell you what everything is. Be good practice for you. So there you go. Enjoy some work there, and let's keep going. Let's try to formalize this. All right. So partial fractions. We're applying this. The context here is rational functions, and in the same way that you might look at, say, I don't know, let's say 7/12. Right, 7/12, you could think of that as some combination of fourths and thirds, right? In fact, what would that be? 1/4. Gotta be 3. And 1/3. So you get 4 plus 3, which is 7, right? So you could think of a fraction as being decomposed into a sum of different fractions. That's kind of what we're doing here with our rational functions. We're writing them as a sum or difference of fractions whose denominators are prime polynomials, okay? And so we're going to look at this, these 3 cases. There are more cases. You could generalize this to just be obscene, but we're going to limit ourselves to these 3 cases because once you see these, I think you can appreciate what the others would be. So the first would be that there are non-repeated linear factors in that denominator. The second, repeated linear factors. And the third, a non-repeated prime quadratic factor. All right. So let's take a look. Let's start with non-repeated linear factors. Now don't be intimidated here, right? My denominator can be completely factored, okay? And what I'm gonna do is I'm gonna rewrite this as this sum. Now think about it. If you were to find a common denominator and the denominators have no common factors, then that common denominator is just their product, right? And there you go. All right, let's see how this works. So we've got 2x squared minus 1 over x cubed minus 2x squared minus 15x. My first job is to take this denominator and factor it. And so I have x times x squared minus 2x minus 15. And then x minus 5, x plus 3. All right. So what I'm going to do now is I'm going to set up this expression. I have 2x squared minus 1 over x times x minus 5 times x plus 3 equals, and here I have my three denominators. Notice that each factor becomes a denominator. Common denominator is just their product. Now, since my numerator must be of degree less than my denominator, and my denominators are all first degree, I know that these are all constants, okay? And so now we go to work. So getting a common denominator, right? This a would get multiplied by x minus 5 and x minus 3. This b would get multiplied by x and x minus 3. And c would get multiplied by x and x minus 5. And then that sum of the numerators would just be the numerator over here, 2x squared minus 1. So let's write that out. I have a times x minus 5 times x minus 3 plus b times x minus 3 plus c times x minus 5. This equals 2x squared minus 1. All right. I'm going to do myself a favor, and rather than expand all this out and equate coefficients, I'm going to start with my x's and say, all right, well, what if x is, say, 0? Now, what does that do for me? Well, if x is 0, then the bx x minus 3 is 0, and the c times x minus 5 is 0. Leaving me with, well, negative 5 times negative 3, 15a, equals, well, on the right-hand side, right, 2 times 0 squared is 0 minus 1, negative 1. So I get a is negative 1/15. All right? Now let's just continue to be strategic here. If I want to find b now, well, I'm going to let x equal 5, because if I let x equal 5, that's going to get rid of my first term and my third term. And so if x is 5, I've got 5 times 5 minus 3, I've got 10b equals, and then the right side of that equation, well, x is 5, so I've got 25 times 2 is 50, 10b equals 49. So b is 49/10. And then while I'm at it, let's find c. And I can do that by letting x equal 3. So 3 times negative 2, so negative 6c equals, and then over here, 18 minus 1 is 17. So c is negative 17/6. Well, look what happens to my integral. This integral now becomes Well, negative 1/15 over x dx plus 49/10 over x minus 5 dx plus negative 17/6 over x minus 3 dx. Well, we know how to do this. This is going to be negative 1/15 ln absolute value x plus 49/10 ln absolute value x minus 5 minus 17/6 ln absolute value x minus 3 plus a constant, okay? And if you want, you could combine these, right? You could make these coefficients of the natural log exponents, and you could simplify this into a single natural log. There's nothing wrong with that. But there you go. All right, what if there are repeated linear factors? Well, that would be this case. Let's see what happens. So again, I'm going to take this denominator and I'm going to factor it. Okay. And so I get x times x minus 1 squared. Well, what I'm going to do in this case is this. I could have an a over x, and let's come back here and look. Right, I'm going to account for all the lower degrees of the factor that I have. So b over x minus 1, and then c over x minus 1 squared. All right, and then of course we do just like we did before. So my common denominators, right? I'll have a times x minus 1 squared plus b times x minus 1, and then c simply times x, that's going to equal x squared plus 2. All right. And so if we want to be creative here, trying to figure out what values are what, I could start by letting, I don't know, I could choose, say, x equals 0. So if x equals 0, then I'm just left with, right, a, and then 0 squared plus 2. It's just 2. Maybe now I'll let x be 1. If x is 1, then I'm going to have c, right, because that'll get rid of the a, the b. C times 1 is going to be 1 squared plus 2, which is 3. And then I still need to get b, but I can do that fairly easily now that I know what a and b are, right? So let's go in and do that next. So I don't know, maybe we can let x be 2 just to simplify things a little bit. And so if x is 2, then we have a is 2 times 2 minus 1 squared plus b times 2 minus 1 plus, and then my c is 3, so 3 times 2, and this equals x squared plus 2, which is what, 6? Yeah, so what do we get over here? 2b plus 8 equals 6. So that's negative 2 divided by 2, b is negative 1. Okay, and so my integral becomes plus x. Let's see, this integral becomes, I'm going to write it down here, 2 over x dx plus, my b is -1, so -1 over x minus 1 dx, and my c is 3. 3 over x minus 1 quantity squared dx, okay? And so now we are on our way. We've got 2 ln absolute value x minus the natural log absolute value x minus 1. And then what about the 1 over x minus 1 quantity squared? How do we handle that? Well, let's see what we get. Let u be x minus 1, which makes du dx. And so we're really integrating u to the -2. Okay. And so this becomes 2 and then minus 3 u to the -1, right? So x minus 1 to the -1 plus c. Which, if you want, make things look a little prettier, I guess. Minus 3 over x minus 1 plus a constant. All right? Okay. Well, what about the next case? We have a non-repeated quadratic factor. So in other words, this denominator down here is prime because the numerator has to be 1 degree less or lower, 1 or more degrees less, then my numerator needs to be linear or constant. And so that's going to look like this. So again, x cubed minus x squared plus x, I factor this, and I get x squared minus x plus 1, which of course, x squared minus x plus 1 is prime. I can't factor that anymore. And so I have x squared plus 1 over x times x squared minus x plus 1 equals a over x. And then here's my other numerator. It has to be linear or constant, so bx plus c, okay? And then we just continue like we've been going. So a is going to get multiplied by the other denominator. And then bx plus c, whoops, is going to get multiplied by x. So we get x squared plus 1, okay? And so again, I could let x be 0, and if I do that, that's going to get rid of the second term, so that I'll just have a times, well, 0 minus 0 plus 1 is 1. And then on the right-hand side, 0 plus 1 is 1. So I get a equals 1. That's nice. Okay. And then we could let, I don't know, we could let x be, just pick something else and let's see what happens. So maybe x equals 1. And so if x equals 1, then this first term up here is going to be a times 1, but a is 1, so that's just 1, plus b plus c equals 2. So b plus c is 1. And maybe while we're at it, we let x be -1. So if that's the case, let's see. 1 minus -1 is 2, plus 1 is 3. So we're going to get 3 plus, and then negative b plus c times -1 equals 2. And so that's going to give me b minus c equals -1. And so if you look at what we've got here, got b plus c equals 1, b minus c equals -1. Let's add these, and we'll get 2b is 0. So b is 0. If b is 0, then c has to be 1. Okay? So now I know what this integral is going to look like when I decompose it. I am going to have, let's see, where am I? Where's my a? Oh yeah, I'm going to have a 1 over x dx. And then my c, right, turned out to be 0. And so since my b turned out to be 0, then my next term will just be 1 over x squared minus x plus 1 dx. Okay. And now, you may not like this, but the second integral is not necessarily the easiest thing to see. But I'm going to complete the square. And in doing that, we're going to see that it's actually a particular form. So when I complete the square, and again, this is something that if you're not following, you probably want to pause and fill in the holes. So this is the completed square. I don't like the term FOIL, but if so many people know it, that if you did use that, then right, 1/2 x, 1/2 x, add those, you get 1. So since it's negative plus -1/2 plus -1/2, you get -1x. And then when you multiply, you'll get a 1/4, and then plus that 3/4, there's the 1. And so what you should recognize is that this is actually the form, if I let u be x minus 1/2, so du is dx, then you actually get this inverse tangent, right? In fact, earlier, in one of the earlier lectures, we did the integral of 1 over x squared plus a squared. So that's really what we have here. Inverse tangent u, but what's my u? My u, of course, is that x minus 1/2. Okay, x minus 1/2 And so we have x minus 1/2 over my a. Of course, my a is root 3 over 2. And then all this times 1 over a. So 2, whoop, I didn't give myself enough room. Plus 2 over root 3. And plus a constant, okay? Yes, we can clean that up, make it a little more palatable. 2 over root 3, inverse tangent. And then what was that? 2x minus 1 all over root 3 plus a constant, okay? So, is it the prettiest thing in the world? No, but it's doable. And yes, we're really heavily relying on all the pieces we've looked at up to this point. So please don't be intimidated by that, right? It just means that we have to know what we know, all right? Okay, let's put all these together. We got 2 more examples to look at. This first one, you'll notice that the degree of the numerator is larger than the degree of the denominator. So we need to do some work on this, namely long division. If you don't remember long division, I'm about to show you. Of course, calculus is that course that brings up everything you've ever learned, it seems like. And I've always thought of calculus as finding what you might be weak at, and then just kind of like if you have a hole in a sweater and you put your finger in that hole and start to stretch it and make the hole bigger and bigger. That's kind of what calculus does to any part of our math education that's somewhat Swiss cheese. So we got to fill those holes in. So let's do that here. So when I divide, right, look at x squared, 7x. Well, I look at x squared and 4x cubed, but x squared times 4x is 4x cubed. And so I line up my terms, right? So 4x cubed, let's see, plus 4x squared minus 24x. And we're going to subtract all this. And so negative 8x squared. And 7 minus negative 24 is going to be plus 31x, and then minus 9. At this point, I'm going to look at x squared and negative 8x squared, so minus 8. So negative 8x squared minus 8x plus 48. And we subtract. 31 minus negative 8 is 39x, and negative 9 minus 48 will be negative 57, okay? And so that's going to turn this integral into 4x minus 8 plus 39x minus 57 over x squared plus x minus 6 dx, okay? And so what we can do now is, I'm going to actually get rid of this just to give myself some room. So I can break this integral up, which is exactly what I'm going to do here. All right. So I've got the integral of 4x minus 8 dx plus the integral of 39x minus 57 all over. And while I'm at it, I'm going to factor this. That denominator right there. Plus 3 minus 2. Okay. So let's just focus on this integral. So 39x minus 57 equals, well, these are linear factors. So I have a over x plus 3 plus b over x minus 2. Again, get that numerator from combining and then be strategic, right? Let x equal -3. So that if x is -3, the b is gone. And you've got a -5a equals, and then let's see, we have 39 times -3. And then what, minus 57? So let's see what we get there. So 39 times -3. You get -174. So A is 174 over 5. And then we're going to do the same thing for B. Let's let x be 2 to get rid of the A. And so we have 5B equals, and then 39 times 2 minus 57 is 21. So B is 21/5. Oh, good. Now I can take this integral and write it as follows. So I'm going to have 4, let me give myself some room here, times the integral of x minus 8 dx plus, and then we have 174 over 5 all over what? A gets x plus 3 dx. And then plus 21/5 over x minus 2 dx. Here we go. So x squared over 2 minus 8x plus 174 over 5 natural log absolute value x plus 3 plus 21/5 natural log absolute value x minus 2 plus my constant. And if you want, yeah, you can clean this up. I'm going to leave it, but yeah, you could, well, all right. I'm sure that you're looking at this bothered by the first term at least. So minus what, 32x plus all this fun stuff. And so there we have it. Okay. Hey, let's do one more. Uh-oh, what's going on here? Well, watch this. We'll let u be cosine x. So that my du is negative sine x dx. What does that do to my integral? Well, it gives me -1 over u minus 1 times u squared plus 1 du. Oh, so it looks like I've got some factors I can play around with. Okay. And so I have a -1 over u minus 1 u squared plus 1 equals a over u minus 1. And then u squared plus 1 is quadratic. So that numerator could be BU plus C. Okay. And now we proceed. So A times U squared plus 1 plus BU plus C times U minus 1 is equal to -1. Okay. To start off, I'm going to let U equal 1 so that I get 2A, and then the second product, right, will be 0. So A is -1/2. Okay. Now, I think I'm going to let U be 0, because what that does now is that, right, A times U squared plus 1, that's going to be -1/2, plus, and then if U is 0, that kills the BU, right? So I just have C times U minus 1, which is going to be C times, well, -1/2 minus 1 is -3/2. And that equals -1. So let's see, -3/2 C equals, and then add 1/2 to both sides, -1/2. So C equals, what is that going to be, 1/3? There we go. And then if C is 1/3, should be able to find B pretty easily now. If A is -1/2, C is 1/3. I don't know, we could let U be 2 if you want. I'm just picking any old values here. So if we get 2, then let's see, 2 squared plus 1, that's 5. So -1/2 times 5, we have -5/2. And then plus, well, if U is 2, this 2, U minus 1 becomes 1. So we just have 2B plus C, which equals -1. And so what are we going to get now? Let's see. We'll have 2B equals, let's see, -4/3 plus 5/2. 7/6. So B is 7/12. All righty. Now we're ready to go back to our integral. Okay, so my A is -1/2. And then we have 7/12 U plus 1/3. All right. Okay, so -1/2 natural log absolute value of U minus 1 plus, and then what I'm going to do here is I'm going to break this up. Let me do it like this. We have 7/12 U over U squared plus 1 du, and then plus 1/3 integral, sorry about that, 1 over U squared plus 1 du. All right, so let's see. We have -1/2 natural log absolute value U minus 1. And then this U squared plus 1, I could do a U substitution on that if I wanted. All right. And then integral of U squared over 1. Well, we remember what that is, right? Integral of 1 over U squared plus 1. That's our inverse tangent. Okay. And now we're ready to go back and replace our U's. So cosine x minus 1. Plus 1/3 plus a constant. All right. All right, so I know that these problems can be lengthy. I know that using integration by parts, right? This is very telescoping. Like we're using integration by parts, but then we see we might have some type of inverse trig, whatever it is. Just be patient, okay? You have a lot of tools at your disposal, and instead of looking at this and getting, breaking it into your partial fractions and then saying, oh my gosh, now I have to do what? It's all just creating a big picture, okay? Think of it as built-in review if you want. The more of these you do, the more natural they become, the more adept you get. So be patient with the process, work some problems, and I look forward to coming back together with you guys and talking about the next techniques. All right, happy studies.